So we learned how to calculate the difference in mass, but we're going to be using another unit. It's called MeV. It's million electron volts. So this is a convenient unit because we can take a small amount of energy and make it into 1 MeV. So 1 MeV equals 1.6 times 10 to the minus 13 joules. So we're given this, and then we're asked for what's called the binding energy per nucleon for oxygen 16. So we had to create an oxygen 16, and we had gotten the change in mass as a minus 0.1366 grams per mole. So now that we have this as our mass, we can use delta E equals delta mc squared to find the joules per mole. So we take our mass, our change in mass, minus 1.366 times 10 to the minus 4 kilograms per mole. We multiply it by the speed of light squared, and we get a minus 1.23 times 10 to the 13 joules per mole. So in this case, we want per 1 nucleon. So we need to convert from moles to a number. We're going to use our answer, which is a minus 1.23 times 10 to the 13 joules per mole. We use Avogadro's number because 1 mole would be Avogadro's number of nuclei. So this is going to give us nuclei. Moles are going to cancel. We're going to still have joules. So that's how we get our units of joules over nucleus. And this is our answer. Minus 2.04 times 10 to the minus 11. Now we're going to use the conversion for the million electron volts, the MeV to joules. We have 16 nucleons per 1 nucleus. That was 8 protons and 8 neutrons. So we have our answer in joules per nucleus. And then we're going to convert using our conversion factor for our MeV. So the joules is going to cancel. And then for 1 nucleus, there's 16 nucleons. And that's how we get this answer. 8 MeV per nucleon. So it's common to use the answer, to use the MeV in million electron volts, MeV. And then the binding energy, we don't care about the negative. The binding energy is just the numerical value. So we just kind of ignore the negative. So the binding energy is a positive value. So typically the question will ask you just for the binding energy and MeV, and they will give you whatever it is that you have to make. So in other words, the question will give you anything on the periodic table is fair game, any isotope. You'll be given this. You have to know that this is your product and that you will always make it from a hydrogen and from a neutron. So for our particular example, we have 2 neutrons and 2 hydrogens. And if you notice that these values are from the periodic table. So we want our change in mass, we want our product minus the sum of the reactants. We need to use our stoichiometry. So this 2 goes here, this 2 goes here, and so this is what we get for our change in mass for this particular problem. We can use a conversion factor of 1.66 times 10 to the minus 27 kilograms per AMU. And when we do that, then we will have the units we want. So the AMUs are going to cancel, and you're going to get kilograms. We end up having a kilogram meter squared per second squared per nucleus. We need to remember that 1 joule is a kilogram meter squared per second squared. And so our change in energy as far as units is joules per nucleus. So this is our numerical value for our change in energy, joules per nucleus. We need to also remember in this case, we have 4 nucleons, 2 neutrons, plus 2 hydrogens. That's going to be 4 nucleons. And so our units are joules per nucleus. For every 1 nucleus, there will be 4 nucleons. And then we're changing our joules to MeV using the conversion factor. So the joules cancel. So we get the binding energy for this example is 7.1 MeV per nucleon. So this is the typical way to work out this problem. You'll be given any possible atom here. You always use the hydrogens and the neutrons, and then you have to determine how many moles of each. If you follow through with these steps, then you'll get the MeV per nucleon. So the energy is released to the surroundings and is therefore negative. However, the nuclear binding energy is the numerical value, and so we take the absolute value of the delta E. Okay, now we have some concepts. We have nuclear fusion, which is defined as combining 2 light nuclei to form a heavier, more stable nucleus. So for example, this is an equation that would be an example of nuclear fusion. These are your 2 light nuclei. This is your more stable nucleus. We also released a neutron and energy. The fusion of 2 light nuclei can produce large amounts of energy. So for example, the sun is composed of 73% hydrogen, 26% helium, and 1% other. And it gives off energy from the fusion of protons to form helium. So don't confuse fusion with fission. Those are 2 different concepts. Fission is splitting a heavy nucleus into 2 nuclei with smaller mass numbers, 2 or more. So for example, uranium-235 undergoes fission when it captures a neutron. So fission is the process that would happen with uranium-235 or plutonium-239, and that would happen in atomic bombs. So looking at applications of radioactivity, we have the Curie, which is 3.7 times 10 to the 10 disintegrations per second. It's a rate. A rad is a radiation absorbed dose. It measures radiation doses. So 1 rad is 1 times 10 to the minus 5 joules per gram tissue. The higher the energy, the more damage to tissues. Another unit is the rem. It's Rankine equivalent man. And 1 rem equals 1 rad times the relative biological effectiveness. And the relative biological effectiveness relates to how much damage can be caused by the radioactivity. So nuclear medicine, briefly, for diagnostic uses, you'd want to have a short half-life. You want to emit gamma radiation. You want to have the highest specific activity. And the becquerel is defined as the number of radioactive transformations per second that occur in a particular radionuclide. So that would give you an idea of your specific activity. So characteristics needed for therapeutic uses, sure, the half-life should not cause extended hospital stay. Alpha and beta should be of sufficient energy to penetrate the lesions. And also you want gamma, so you could facilitate the assessment of the targeted tissue. So just a few examples. So these are a few diagnostic examples. So you could follow blood flow. You could do lymphoma imaging and renal imaging. You could look at colonic transit and white blood cell scan for a source of sepsis. You could do a thyroid scan and a brain scan. So some therapeutic agents, hypothyroidism, you could treat that. Prostate cancer, non-Hodgkin's lymphoma, you could treat that.